Lesson 30, Newton's Laws of Motion. We have two objectives for this lesson. The first is to state, explain, and apply Newton's laws of motion. And the second is that since Newton's second law takes on the form of an equation, you want to be able to use it to solve problems. So looking at Newton's first law, it's called the law of inertia, and you'll usually see it written something similar to this. An object at rest stays at rest unless a force causes it to move, or in this case, accelerate. And an object in motion will stay in motion at a constant velocity unless a force causes it to accelerate or decelerate. Notice that it's at a constant velocity. That would be a constant motion. If you recall, velocity is the speed of an object and its direction. So both of those make up a constant motion. So if a force causes it to change its speed or to change its direction, either one, a force has to do so. Now, these 2 points can be simply put down to one simple statement. An object's motion is constant unless a force changes it. Whether it's at rest or in motion, a force must change the motion. It gets its name, inertia, from the term inertia, which means an object's resistance to change. So, since the object's motion doesn't want to change, we call it a law of inertia. Now, inertia is also a way of measuring an object's mass. When you first got a definition for mass, we said it's how much matter makes up an object. But that amount of matter is going to resist changes to its motion. Let's take a look at an example. Let's compare two cars, or two vehicles. Let's say you have an 18-wheeler rig and a Ford Focus. An 18-wheeler rig has a lot more mass. Therefore, it needs a much bigger engine, and also it uses air brakes. The bigger engine gets it moving, and the air brakes help stop it. In other words, change its motion. The Ford Focus has a much smaller engine, and it just uses regular brakes. It doesn't need as much force to change its motion. So the amount of mass something has is directly related to how much inertia it has. Newton's second law says an unbalanced force will cause an object to accelerate or decelerate. And this can take on the form of an equation, F equals m times a. A very simple formula, but one that does get used a lot. Since there are three things in this formula, we could write it in the form of a triangle. Now, I didn't put down what each of these stand for because you should be familiar with each of these already. F is force, m is mass, and a is acceleration. You should also be familiar with the units. F, force, is measured in newtons. M, or mass, is measured in kilograms, and a, or acceleration, is measured in meters per second squared. When you put this formula on your formula card, it will actually be the last formula to go on your formula card at all. It's also the last formula to go under mechanics. Now, one of the things to note is that we've been using a newton since lesson 5. And at that point, I told you that a newton is actually not a fundamental unit. And this is why. A newton actually comes from this formula. A newton comes from the fact that we're taking a kilogram and multiplying it by a meter per second squared. So just like a joule is a newton times a meter, or a watt is a joule per second, a newton is a kilogram times a meter per second squared, a derived unit. Now let's take a look at an example using this formula. It says a force of 20 newtons gives a stone an acceleration of 4 meters per second squared. What is the mass of the stone? So if we start by taking a look at what we're trying to find, what is the mass? We immediately run into a problem, which is this. Ever since lesson 5, you've had a formula to solve for mass when you had the object's weight. Or in lesson 12, you used the density formula to find the mass. You now have another formula that you can use to find mass. So this is another case where it is very important to read the problem carefully to see what information is given. Just as in the scientific method, gathering information is very important. So we can see that we have a force of 20 newtons and an acceleration of 4 meters per second squared. Since we have a force and an acceleration, not a weight nor a density, that indicates that we want to use Newton's second law. We can then substitute in the values and get an answer. Now, you could put the units in, but you have to remember that a Newton is actually a derived unit. That's how we get kilograms out. Lastly, we have Newton's third law of motion. It's more commonly called the law of action-reaction, which says for every action, there's an equal and opposite reaction. It is probably better stated that forces always occur in pairs. Now you might be wondering, what does this have to do with laws of motion? Why does it even deal with motion? Well, it's because of this that most motion occurs. Think about it. When you're walking, you have to push your foot against the ground. The ground pushes back. You push against the ground pushes back. Action, reaction. If the reaction of the ground pushing back didn't occur, you wouldn't move forward. Think about trying to walk on ice. When you push your foot against the ground and your foot slides, you don't go forward. You actually go down. Another example would be when you're swimming. Your hands push against the water and the water pushes back. This is what allows you to go forward. The action of your hand pushing against the water and the reaction of the water pushing against your hand is what allows the motion to occur. So those are Newton's 3 laws of motion.